So it's my pleasure to be visible on the camera and also to introduce Bruno Cavalar, who will tell us about monotone circuits, constant circuits, and their relations. Please.
Yeah. Thank you for the introduction. So yeah, the main interest and the main topic of discussion today is the circuit complexity of Boolean functions. I'm not so sure how familiar with all the basic concepts everyone is, and probably most of you are. But so yeah, the circuit complexity of Boolean functions, and maybe I don't know if I can show you, but a Boolean function you might know is a mapping from n-bit binary strings to 0 and 1. And our interest with this is you can model, let's say, you can model decision problems as Boolean functions or sequences of Boolean functions. And when you do this, you can also talk about the circuit complexity of computing those functions as a measure of the complexity of the underlying computational problem. And when you have circuits, you're talking about these DAGs, which are labeled with logical operators, right? In a natural way, they compute some function. And then at the bottom, you have your inputs, right? You can have, let's say, negations at the bottom, right? So the measure, one of the main measures we would care about here is the size, which is the minimum number of gates to compute a function. You can also talk about the depth, which is the minimum path between from the input to the output gate. Okay. Right. And one very important prominent class of Boolean functions is the class of monotone Boolean functions. Okay. I don't know if the board is okay. So, yeah. This is not written. But so what I want to say is you can say that you can write that x is at most y. There's a partial order over binary strings, which is satisfied even only if xi is at most yi for every entry. Okay, and saying the function is monotone if it preserves or respects this ordering. So f of x at most f of y whenever x is at most y. It's very hard to read, but I think the idea is you're receiving an input, and a binary string as an input, and thank you. You have a binary string as an input, and let's say you accept this input. Whenever you turn a 0 to a 1 in your input, you should continue accepting it. That's a definition of a monotone Boolean function. Two prominent examples of monotone Boolean functions. Thank you. Yes. Well, maybe you want to have this problem again. Two prominent examples of monotone Boolean functions are, let's say, the majority function. You just want to know if the majority of the input bits are 1, or the k-clique function. You receive a graph as a J system matrix, and you want to find out whether there's a clique containing it. Right? If you add more edges, you continue having a clique. So that's the idea of how a monotone Boolean function is. And when you talk about monotone Boolean functions, one model you can consider for computing them is monotone circuits. So the main difference here between a monotone circuit and a monotone circuit is usually only that you don't allow negations. So here you have a monotone circuit with negations. Monotone circuit doesn't have negations, and has lots of applications in all sorts of areas in computer science, cryptography, logic theory. Particular interest here, proof complexity, optimization, lower bounds, so on. And one motivation for this work is trying to understand really how much power negation the having negation buys you over computing monotone Boolean functions. And as Zukina puts in his book, he believes that the main mystery, or the main that we really need to achieve to be able to prove hardness results for computational problems is really to understand what's really what are negations doing, what is this mystery? Because as we briefly review, we do have strong lower bounds for monotone circuits, or circuits without negations. Okay, so here is the suffering of the monotone circuit class. I mean, it's something that if you know circuit complexity, you've heard a lot that monotone circuits are useless. They don't do anything because there are these monotone functions obtained by Tardash. They can be computed in polynomial size, but polynomial size circuits, but it requires exponential size monotone circuits. Really here highlighting the weakness of monotone circuits. Later on, Raz and Wittgenstein show that there's a monotone function even below here in NC2. So this means that it's a circuit with log square depth and fanning 2. Okay, so it's a parallel circuit, and it can compute something that's even circuits with square root of n depth. So it is like exponential size formulas. Monotone formulas cannot compute. And by formula, I mean a circuit where the fan out of the gates are 1, so it looks like a tree. And just recently, the separation was improved both ways. So we improved the upper bound of Tardash and the lower bound of Raz and Wittgenstein. So monotone function NC2 with exponential monotone circuit lower bound, not only a depth lower bound. Okay, and this sort of weakness of monotone circuits was explored also in the context of low depth or constant depth. So one of the objects we'll be interested here today is the constant depth circuits, as the title said. So AC0 is how we name this class of circuits, which are which have constant depth, and to avoid it being a trivial class, we require that the fanning of the gates or an end are unbounded. Okay, so it can have unbounded number of inputs going to any gate. And Ajtai and Gurevich in 1987 proved that there is indeed a monotone problem in AC0 that cannot be computed by its corresponding monotone model. And only recently this was extended to an exponential lower bound, but it's still for monotone AC0 circuits. But is that the whole story? I mean, can we just stop with the weakness of monotone circuits and say nothing else? There are some contexts where monotone circuits. Yes, please.
On the previous slide, what was the for every D?
Yeah. So the question is, if this is for every D. Yeah, for every D, you get this. You get a lower bound like this. So if you go for a larger depth, you will get a worse lower bound. But here the depth is fixed. I didn't say it, but it's one function in AC0 depth 3 even.
The little O does not have D.
Well, good question.
What was the question?
Oh yeah, the question is this little O here. Does it have a factor of D there? I'm not sure. You might have factors. Yeah, so I don't know. I don't remember. Yeah, sorry. Yeah. So I was going to say there's some context where monotone circuits can do things that the previous picture would suggest may be surprising. So it can solve constant satisfaction problems when you have a three-width bound or graph theoretic bounds on the graph of the constraints. Okay. And it has been shown already that if you have one-way function, then you can have monotone one-way functions computed by monotone circuits. Okay. And also some contexts, you can actually remove the negation. You can simulate non-monotone world in a monotone world. So very simple observation is just that if you have a DNF, you can just remove the negations computing a monotone function. and you get a monotone DNF. More recently, Ben Rosman has shown that every graph property of graphs which are preserved under homomorphisms, which is computed by AC0 circuits, can also be computed even by monotone DNFs. So you can remove the negations entirely. Yeah.
In the first and the second line, you make a distinction between poly versus non-poly. I mean, in the first line, on the right-hand side.
Yeah, in the first line, it's any size because it's so you don't lose anything.
I see.
Yeah.
Same size.
Yeah. Good. Here, I don't know if it would work for larger size. And also, as is also a very interesting observation, is that if you have a slice function, so it's a monotone function that it only does interesting computation on a single slice of the Boolean hypercube. So over that slice, it always outputs 1. Below that slice, outputs 0. In that case, yeah, negations are powerless. So so you have this mystery of negations, right? You have on one side you have this exponential or superpolynomial lower bounds for functions here in NC2, like recently, and you have these things in AC0 here, which you only get this monotone AC0 lower bounds. So can you go very low here in the non-monotone world and very big in the monotone world in respect to lower bounds? So this was concretely asked by Grigni and Sipser in 1992. Is there can every monotone function computed in AC0 be computed by polynomial size monotone circuits? Let me say that I mentioned that in the algebraic world, it has recently been shown that such a simulation is impossible. So in the algebraic world, I mean by algebraic circuits computing polynomials, right? But we don't know the answer yet for the Boolean world. You can present some progress in that question. The first theorem is that there is a monotone function in AC0 which requires polylog depth to be computed. So this is for every k. So for every k, you get a different function, but it continues to be in AC0, but you get a lower, bigger depth lower bound. An interesting thing about this result is it also holds for graph properties. So there is a monotone function which is a graph property which cannot be collapsed to low depth monotone circuit. And this strengthens a recent result of Demi Kupperberg, who showed that, like I showed the Ajtai and Gurevich separation for graph properties. And this improves the Ajtai and Gurevich separation because AC0 is containing in log depth, right? And it gives a contrast between the class of graph properties and graph properties which are preserved under homomorphisms. As we just mentioned, this class of properties preserved in homomorphisms can be computed by, you can collapse it to low depth, but not the graph properties in general. So, and what about monotone circuit size? Here we can just get a depth lower bound. Can you say something about circuit size? And the answer is yes, but you do have to give some extra power to AC0. So again, for every k, there is a monotone function AC0 parity, and you get quasi-polynomial size lower bound. This is incomparable to the previous result. We get a better lower bound, but the upper bound is slightly worse. Okay? And it's almost solving the question of Grigni and Sipser, except for that parity here. Okay, and gives the first separation that is between constant depth circuits and monotone circuits. So, can we hope for better monotone simulation? So there's still this parity there. Is it possible is that you just remove the parities and all of a sudden we get a continuity? So one first simple observation you can make is that using some standard techniques like switching lemma, you can take any monotone function AC0 and put it in slightly non-trivial upper bound. And it's even achieved by monotone DNFs. Okay. But we can show that if these simulations are possible, if we can actually simulate non-monotone circuits with monotone circuits, and you get some striking consequences. So first, if you can put every depth-3 AC0 circuit in, can compute it with a polynomial size monotone formula or log depth monotone circuit, then you can get this monotone function, some function, not necessarily monotone, in NP, that cannot be computed by AC0 depth-3 circuits with this much size. And this is an important problem. Has been attempted for a long time because, I mean, first, the best lower bound you know for AC0 depth-3 circuits is through the square root of n. And as Valiant showed, I don't know how many decades ago, if you get something, if you get this lower bound for AC0 depth-3, then you can finally get some lower bound for linear size log depth circuits, right? So this has been we don't know yet how to prove not even superlinear circuit lower bounds, but even lower bounds for linear size log depth circuits, and that would show that. And here I show that if the problem of Grigni and Sipser, if you cannot show the separation that Grigni and Sipser asked, then you can get the NC2 is not contained in NC1, so that the separation of NC2. And similar consequences also follow from the simulation of merely graph properties. So if you could show something like what Rosman showed for homomorphism, graph properties preserved under homomorphisms. And you could phrase that in a interesting way that one of the following two things is true, and NC2 is not contained in NC1, or AC0 is more powerful than polar size monotone circuits. I personally think both of them are true, but maybe this one is easier to prove. The first one. Okay. So then the next thing we do in this work is we revisit the techniques that we can use to get these operations, the techniques that are known for monotone circular bounds and their capabilities. And these main techniques are actually the approximation method and Newton theorems. And we focus here on lifting and shed light on the kind of separations that you can get. We may hope to get from lifting. Okay. So how does the lower bound for a monotone function NC2 that was proved recently is obtained? It's for this function 3x set. So what is this function? It's a monotone encoding of solving linear systems in modulo 2. Okay. Let's say you have n variables, and we'll restrict ourselves to equations with exactly 3 variables. And how many equations of this form there are? There are 2 n cubed of them. We have n options for each of the variables, so n cubed in total, and 2 options for the equality. And the monotone function will accept if the given linear system is unsatisfiable. Okay, so this is monotone because keep adding constraints continues to be unsatisfiable, right? And you can generalize this for any set of Boolean relations. Here I'm just looking at set of K LRE Boolean relations, but you could talk about each of them having different parities, and you do the applications of these constraints just like you did here, and you get some monotone function. And there's some sense in which this captures lifting, in the sense that many of the lower bounds, if not almost all of them, that are more proved for monotone circuits via lifting, they go from you give a resolution with lower bound on a encoding of the S formula, which is a constrained application of these relations, and then this with lower bound for resolution gives a monotone circular bound. The only caveat is that it's also possible to capture less structured functions, which are not CSP functions, by some clever interpolation of the instances. So, for instance, that separation of Tardosh can be obtained via liftings of click coloring, right? And the click coloring formula. If you just did a CSP stats thing, you would obtain an NP complete. Yes.
Can you explain that line above? What is rest with S formula? Sorry.
Yeah. So what's happening here is the following. You take one specific formula, which can be written as application of constraints from the relations in S. Let's say that citing formula, Pigeonhole principle. Okay. And you prove that any resolution proof of this formula requires large width. That implies lower bound of monotone circuits that compute that solve systems on S. The formula disappeared now. You just got the relation S. So yeah. So the existence of some formula for the relations of S, which requires larger resolution width, implies that CSPs over this set of constraints are hard.
Okay. What exactly do you mean by captures lifting?
Captures, so that's why I put in some codes here. Captures in the sense that most of the monotone circular bounds, like 3x or SAT, for instance, or those for connectivity or gen, they're like this. They're equivalent to this. But there's the caveat, so that I almost say captured totally, because sometimes if you look at the instances that are generated, they are not all the entire instances of CSP. They in some way they are still hiding this S formula there. So sometimes if you're smart enough, you can get an easier to compute function, like the Tardosh function. Good. So what are the limits that can show for this? Would say the direct approach via lifting and CSPs. Direct because you just take whatever CSP function you get from lifting, and you try to get some separation. So the first thing we show is that if you have a CSP problem that is not computed by polynomial size monotone circuits, then right, you have a lower bound for it, monotone circular bound for it. Then you also have a sort of non-monotone lower bound, as much as you can hope for. You show that it's parity L hard. Okay, under 0.1 reductions. And if it's not computed by monotone NC1, then it's also log space hard. Okay. So I had hoped to, I don't know, maybe it has a little and I just some hierarchy here to help those who are not so familiar, but you have AC0 here at the bottom, right? And then AC0 parity. I'm just going to here to MC1, and then log space, NL, parity L, and NC2, and then P, and I just go to. Okay. So we are saying that if you have a monotone circular bound that's super polynomial, then you have to be here or above. And if you have this depth floor bound, super logarithmic depth floor bound, then you must be here or above. Right? So you can't be here in AC0 or AC0 parity. Right? Right, so in CSP that is hard for monotone circuits is as hard as 3x or set. As we'll see, 3x or set is parity hard. And the way we do this is by showing a monotone dichotomy for CSP set. So if you've seen those dichotomies for CSPs, the first one that was shown 70s by Schaefer is that every Boolean CSP problem is either computed by polynomial time algorithms or is NP complete, right? And then we can show some similar but a complete and unconditional picture of the hardness of these problems, and unconditional because it's not on the hypothesis that P is not equal to NP, you actually show an lower bound. So here's a picture of by Allender, Bolen, Immermann, Schnur, and Vollmer. Maybe in the second part of the talk, we'll be able to explore a little bit what's going on here. But this is a full classification of all types of CSP problems that exist, all types of constraints constraint systems you can create. And you can classify exactly those are NP complete. These ones here at the bottom, and the green ones parity complete, so on. And what these things are doing is they're capturing somehow the symmetries, how much symmetry you have in your system of constraints. So the more symmetric you are, you'll go above in the hierarchy, right? You have more symmetry, so you can explore that symmetry and you can solve the problem. Less symmetry, less structure, then you get you become harder. So in our picture, we get that picture I said. We can name those that are solvable with polynomial size monotone circuits. They're the purple ones, and those here with the green and the lines are those that require exponential size monotone circuits. Okay. And also for monotone depth, we also prove that coupling for monotone depth. So there are some of them that are computed with polynomial size monotone circuits, but they actually require a large depth. And the other ones that are yes.
When do you actually go on edge for CSPs? How should you interpret this?
So the edge is saying that the set of symmetries here is contained the set of symmetries there.
Oh, okay.
I have not defined symmetries, but maybe we will in the second part.
Okay, thank you.
Good. So that's what I meant. Like we have this the symmetries, and there's a way of kind of making a reduction from there to below.
Right. So it's like it's a lattice when the order is the symmetries.
Yeah.
Yeah.
Right. So I guess we even have some time to sketch some of the proof ideas. And in the CSP section, which is more technical, we can discuss the second part. Right. So how do you separate this zero parity and polynomial size monotone circuits? That upper bound in situ just comes from Gaussian elimination. You can solve in your system in situ, right? And the lower bound is obtained by logkn. Now, if you just do this padding trick and depth reduction, you would get a polylog log depth circuit and polynomial size computing this. So padding, I mean, just you create this silly function, a bunch of variables you're ignoring, and you compute the same problem, and to get from NC2 to AC0 to as little depth as you can, while still preserving a super polynomial lower bound. That's the best you can do. But then, of course, our question is, can we get depth constant? It doesn't matter that this is maybe even useful for maybe possible practical purposes, but not constant depth. So the crucial observation is the 3-vector set can be computed by polynomial size span programs. Probably won't define span programs, but this is I have some slides at the end. I can show how to do this. This is not so difficult if I define what span programs are, but this is the same thing as this class of that I wrote here, ParityL. So what is ParityL? So you can think if you have like a non-deterministic log space machine, right? But instead of accepting if there is accepting path, you accept if the number of accepting paths is odd. So it's a counting machine, and you can put 3-vector set into this class, and some simulation theorem, which is implicit in this paper, which we will can show that you can actually do this depth reduction I can simulate this parity out in the exponential zero parity circuits. So it will be more convenient to think about parity as the model of parity branching programs. Okay, so what are these parity branching programs? You have a graph, and just assume that they are layered. The graph is layered. Okay, so all the edges come from one layer to the left, from left to right. All the layers have the same number of vertices. You have this special start vertex and the special end vertex. Okay, and the edges are labeled with input bits. Okay. When you receive an input, this activates certain paths from start to finish. And if the number of paths from start to finish is odd, then the parity branching program is accepting the input. Okay. So how do you simulate such a model with AC0 parity circuits? So what you do is, let's say you want to get depth D circuit, that D is a constant. And M, here's the number of layers. So you divide the branching program into M to the 1 over D equally spaced layers. Okay. And then you just guess one vertex per layer. Guess, if there's a path, there must be a path going through one vertex for each of these layers. Okay. These red vertices there are the vertices you guessed. And then you count the number of paths that go through each of them. Okay, so you guess one vertex per layer and then recurse into the problem with M divided by M to the 1 over D. In other words, M 1 minus 1 over D. So you recurse into each of these blocks. And okay. So this makes sense. Does this make sense to you? You are summing over all the paths and you're multiplying the number of paths between each part. So and here is a multiplication because our modulo 2 XORs the summation. Through these steps, we arrive at a constant number of layers. Okay, because you're removing 1 over D at each layer. So after these steps, you have this up to the alternations of XORs and ANDs. So you get a constant depth circuits, and this when you get this constant number of layers, you just brute force the number of paths. The size of the circuit is going to be roughly the number of choices you have of vertices. And that's like n per layer and m1 over d number of layers, and that's 2 to the n to the go over 1 over d. So that's if you don't care about how big d is, as long as it's constant, that's very small. Okay. Any questions? Right. Now, so we obtain this regular set is in the sub-exponential zero parity, and obtain an exponential monotone circular bound. And then you can do a padding, and a padding is going to be finally give you the depth bound you care about. So let's talk about then the separation with AC0 and log depth. Is this? Yeah. All right. It's a monotone NCI there. Should I? Can we?
I think we can just click it and move it, or remove it even, right? Don't. If you click the dot, you can remove it entirely. Right.
Okay. Good. Thank you. Right. So. So what did GKRS do? They showed this lower bound for CSPs. We're lifting an S formula that requires large resolution width. And the particular formula they look at is S is a set of linear relations, linear equations, and the formula is citing formula. So here, let's look in particular, let's say a G is a connected standard graph with odd number of vertices. Okay, and they just require that you make an equation for each vertex saying that the sum of the edge variables incident to that vertex sum to 1. This is the same thing as saying that there's a subgraph of the graph in which every vertex has odd degree, but you have an odd number of verses, so that's impossible, right? And other observations is every variable occurs exactly twice in the formula, right? Because the edge is extended to vertices, so the sum of equations gives 0 equals 1. Okay, but this is a more restricted than the 3x or sets. You're looking at linear equations where each variable occurs exactly twice. You can code any system like this as a problem like that. So you can turn that into a hard monotone function. That's the question. And yeah, you just receive a graph G, and you accept if the citing form of the graph is satisfiable. And this is monotone, since whenever you add a new edge, you can always set it to 0, and it will continue to be satisfiable if it was before. And you can do some monotone depth lower bound for it, like similar to the tricks used for perfect matching. And here you can get a clean log space separate bound without a parity. And the proof is as follows. This formula citing of the graph is satisfiable if and only if every connected component of the graph has an even number of vertices.
The upper bound is from constant degree expanded or for any graph?
For any graph. Yeah. Yeah. The graph is part of the input. You're deciding if a given graph is satisfiable, deciding that the formula is satisfiable. So how do you do this? Just notice that the citing form of the graph is satisfiable even only if every connected component of the graph has an even number of vertices. So how is this is true? Well, let's suppose that there's some connected component that has an odd number of vertices. Okay, then we can, as I said before, we can derive 0 equals 1 by summing the equation in the component. So that can be satisfied. Now let's suppose that every connected component of the graph has an even number of vertices. You begin by assigning value 0 to every variable, and then you iteratively choose 2 unsatisfied vertices, find a path between them, and flip the variable edges in the path. Right. So let's say take 2 here. At the end, no edges is in your solution. They're all set to 0. Find 2 that are unsatisfied. Let's say these 2 edges, and they're marked with red colors. And you find a path between them, and you flip the variable edges in the path. There are 2 others there that are unsatisfied, and you find this path and you flip it. So now that edge in the middle is switched off. You have these 2. And do it again. In the end, you find a solution to the citing function. Okay. So the parity of the interpretation never changes, just the 2 vertices that you wanted to satisfy. And since there's an even number of vertices in every connected component, again, it will satisfy all of them. And now you only have this. You have this structural property. You just have to check that every connected component has an even number of vertices, and then you can do using Rango's algorithm for connectivity using log space. Okay. So now again, odd factors in log space. We have this depth upper bound, and just like I showed this simulation of parity L by AC0 parity, you can do L by AC0 clean without parities. So you get a similar separation, but this is not enough to obtain a graph property because odd factors are graph property, but when you do this padding, you break it. It's not a graph property anymore because there are some special vertices which are you can't they don't have this, if they can't represent edges of a graph, if they don't have the symmetry of a graph property. So, but what we do is we efficiently construct a monotone padded graph property. So there's a way of doing a smart padding that you preserve the graph propertiness of a of the original function. Okay. Is this clear? Is it clear why this wouldn't be a graph property? Just do a penny. Okay. So maybe I can describe a little bit how this monotone padding for graph properties works. So how it works? We go from little n verses to capital N verses. So we're going through a graph property on larger number of verses. So what you're going to do is, given a graph on capital N verses, you want to just remove all the isolated vertices. And if there are at most little n verses that are left, and then you put it on the original function, and maybe you pad with some extra isolated vertices if you need it. Otherwise, you just accept. If there are too many edges and the graph has more than little n non-isolated vertices, you just accept. And that's monotone. That preserves the monotonicity. Okay. So how do you just clean this graph and you're computing this subgraph? You want to make sure you can do that in EC0. So if the number n, little n, is polylog of capital N, then you can do that in EC0 using the fact polylog thresholds. You can decide if the number of ones in a binary string is larger than the threshold, which is polylog of the length of the string, in EC0. Even though you can do that in general. Okay. And then use the depth reduction to get an exponential EC0 circuit for Fn, but that's going to be polynomial in capital N. Good. So in conclusion, I get this monotone graph property in EC0, which is not computed monotone in CI. Okay, so some directions are for problems. So we showed that AC0 circuits cannot be computed by monotone functions. There are monotone functions in AC0 circuits that cannot be computed by polylog depth monotone circuits. However, we did not specify depth 3, and in fact, the depth 3 question is still open. We don't know if maybe you can put AC0 depth 3 in monotone NC1. When you're talking about monotone functions, or can you do at least some sort of non-trivial simulations, anything to the little oven? These simple questions are still open. And in the question of Grigni and Sipser, there's a very important question, a very simple one, and highlights the importance of understanding the monotone circuit complexity of matching and that factor. We have this exponential depth or formula lower bound for odd factor, monotone formula is computing odd factor, which is equivalent to this square root of n depth lower bound for odd factor. Can you do a circuit lower bound for computing odd factor? Because odd factor is in log space, that would settle the question of Grigni and Sipser by using the same depth reduction padding tricks. Okay, so can you show an exponential monotone circular bound for this function? Turns out this might be very good and solve some long-standing open questions as well, because this lower bound will also imply an exponential monotone circular bound for perfect matching, which has been open for many decades. That's what I had to say for this part, at least. So thank you.
Thank you. Questions? So if there are no questions, I think we'll take a break. and reconvene in something like 10 minutes for those who want to hear about the second technical task. We're back after the break, and it's going to be immensely exciting to see how we can manage a board talk over video. There's only one way of finding out, namely Bruno will try it. Please.
Okay, thank you. So let's try to show the monotone circuit size dichotomy that I showed in the slides. It takes a while to introduce all the concepts, so I ask your patience and attention. So let's say we have some relation R, RT L, okay, and we have, let's say, a set of n variables. Okay, n variables, and you have any tuple V choices of those variables, L choices. So a constraint application is just going to be this function.
The black marker isn't great.
Yeah, there's a black-blue marker.
The black blue?
I'll take the black-blue.
Okay.
That.
Wonderful.
Yeah, so this is supposed to be FRV. This is Boolean thing. Okay, and this is just going to take Boolean bits, and it's going to output if you look at this particular variables there. So they are in the relation R. Okay, so this is what we call a constraint application. Right? I said that during the talk, but I didn't define it. Constraint application. Okay, does it make sense what it is? So we're choosing variables for the relation. Right. So you can also, as we discussed, you can have a set of relations.
And relations are defined over variables now. So for instance, if I want a clause of size L, that would technically speaking be like 2 to the L different relations depending on my negation pattern, or this is not so important at this point?
The relations will be only defined on the binary alphabet, because basically the relations are like the truth tables of the constraints, right? And I guess by saying this, I don't know if that answers your question.
No, but
So, can you repeat the question then?
yeah, no, I don't know if it's important. I mean, the relations are over variables.
Relations are not over variables. They're over.
Yeah, but, okay, constraint application.
Constraint applications are over variables. Yes. So you look at every constraint application, you can just identify it by as a pair of relation and then a choice of the variables. And now, of course, there must be a hidden n here, which is the variables you're choosing to apply. Okay. Right, and the set of relations. We went through this the talk, like the number of possible constraint applications you have, right? If Li is the RT Ri, then you can have n to the Li constraint applications. Of Ri. Okay. So just for a sanity check, so we are on board the CSP function over the set of relations S with n variables is just going to be the summation here over all the relations of n to the Li. Okay. So here we have a bit for every possible constraint application.
Does it indicate whether this constraint is required?
Sorry?
What's the intention of this bit? It means that in my condition set, this one is present.
The bit is telling you, the bit is denoting that that constraint is in your constraint system that you want to satisfy. That constraint application. Okay.
So I can think of as there are many equations in total, and the bit tell me whether this line of equation is in my input system. Okay.
So that's why you really have to constrain yourself to constant parity. And here we talk about constant parity.
Otherwise, you have many of them.
Yeah.
Oh, and the reason that you're summing now is that you have here you're silently introducing we could have k different constraint applications.
Yeah, we can have NCLI constraint applications of the IF relation, and you can have
Yeah,
K
yeah,
relation.
yes, yes.
K relation. Yes.
Which is what I guess returning to my question was exactly that. For instance, like k sat would probably yield something like 2 to the k relation, right? Because you're operating with the variables.
Yeah. Well, K sat. Yeah, that's true. Yeah, because you can have them. Yeah, that's true.
So basically one relation per negation pattern in your clause. So, yes.
Good. I'll erase this.
And K XOR would have two relations, namely the parity odd, the parity C.
Yes. Which is exactly what we had with 3 XOR. And so talk about clones. Okay. So just denote VF here. Set of all Boolean functions over finite number of bits. So this is not only n bits, it's over the number of bits. This is infinite set of functions. And for any b in VF, finite or not, you can define this, which we call a clone or a closure of B, the closure of B, which is all the functions computed with circuits using B as a gate set. Okay. Two observations. One, B is always infinite. Because you can, I'm saying the functions combined using B as gate set, and you can have like arbitrary number of inputs. So you can have like any projection function, xn. So, and it may not contain the constant functions. So even though you're not allowing zeros and ones for free, they're not allowed in construction of the circuit. 0, 1, you know, closure. Yeah. If B is empty, then should be okay. Because it's infinite. Because in that case it would be like if B is not empty, maybe.
And requiring that B should be in BF minus the constant functions then?
No, I'm saying that when I said it's computed, I'm using circuits. My notion of circuits does not allow zeros and ones. This is the same thing as saying that a function I just thought this would be more intuitive, but it's the same thing that a function is in the enclosure of B, if and only if exists G in B, and H1, HK in B union projections, such that F is G composed of those ones. So this is kind of like, so this is what you mean by you can compose the functions arbitrarily, and then you get a function in the
Because
enclosure.
if in particular your h's are constant functions, then you do have constant in that case.
Yeah, but I'm saying H in B or in projections. So
So if B contains the constant function, then you have constants, but otherwise.
Otherwise, you have like.
yeah,
you kind of-
yeah.
It seems you didn't want to allow that.
No, I'm saying that it may not. It's not that it doesn't, shouldn't be,
Oh,
may not. That's
okay, we do not know that.
yeah. Sorry for lack of clarity. And this is growing processor. It's really a closure. So really B is contained in brackets B. So if B contains the constant, brackets B will contain the constant.
And if B is equal to and or and not, then closure is. the
All
whole
Boolean
thing.
functions. Yes. So observation and or not. So that all Boolean functions. Okay. Other observation or and. Any guesses? What it's on the okay. Right.
So just one last clarification. On the bottom of the board, when you say F is the enclosure of B, is equivalent to say there exists G enclosure of B, if I understand correctly.
Here.
Yeah.
No, probably I mean everything in G and B.
Otherwise, do you allow composition? Probably you allow composition of
F
D.
equals G, or
Because I'm allowing B here as well. So I can compose B.
By that you mean enclosure of B. Because B has only,
so you say B union projections?
We didn't define projections, but I mean, yeah, are we,
Yeah.
is it very important at this point that we
I think
parse the finer semantical details, or are we fine
no, I
with
think
this level
I
of
think we should
understanding?
we think it's okay unless
okay.
but I mean if you're also okay.
Okay.
I think
I'll
that B
just
has a set of gates, and then I, whatever I can build with these gates.
Yeah. Good. Just wanted to highlight this zero as one constant thing because it is important. The 0, 1 thing is important.
Yeah, in particular, I mean, the generation of and or is monotone Boolean functions. Except for the constant monotone function.
Yeah, I
Don't
probably
wanna nag you.
no, that's true. That's an important point. You probably need to include the zeros. In the other case, maybe you could build or ends and negations. You probably could build zeros and ones with the negation, but monotone. Good. Right. So let's talk about go closer to that crazy picture I showed. Talking about polymorphisms and events. So we have R being a K-area relation, and F a function. So we have this other definition. F is a polymorphism. R. Okay. If you have this following for every so you have L bits in the F functions for every L guys in the table of R. Let's say you write this X1 guy here. This will be X1 almost invisible. Let's see if that's better. One, maybe better.
Yeah, but
Good. So this is really the first element from the relation. We're going through, we're writing here the first element of the relation. And parity. It is the same here.
oh, R is a K-ary relation now, and F is an L-ary function.
Yes.
Mhm.
So we will see happens. So just writing these guys here in a matrix form. So what needs to happen for F to be a polymorphism of the relation? This blue is really good. We're going to apply here. I'm going to do it in a graphical manner. We're going to apply F to this. You see, we have L bits here. We're going to apply F. We do the same here in every column. Apply F. Apply F. And then in the end, you require that this this combination of the L guys in the relation continues to be in the relation. So there's a polymorphism or a symmetry, a way of combining satisfying assignments to the relation. That's why you also see that R is an invariant. The relation is an invariant of the function.
Can I ask a very vague question,
Mhm.
which might not have an answer?
Mhm.
Is this in any way related to the fusion method?
When you look, the answer to this question is, I think it might be. First, this is really like what you do with the fusion method, right? But secondly, there's this paper I haven't read by some researcher from Sweden, Gustav Nord. You can look it up online, and he has a paper called Polymorphism and Circuit Complexity, where he studies the connection between this sort of thing and fusion method.
Okay.
But I haven't gone into it yet.
Okay.
Maybe an answerable question, why the name polymorphism?
Oh. I don't know, sorry. Yeah, I didn't come up with the name, and I think invariant makes a lot of sense.
Invariant makes sense.
Okay. Should be an easy question to answer, but I know less about that question than about your own. So an example, this is if you have linear systems, so R is just as we had before, let's say parity, arithmetic, and equal 1. So this is really those that satisfy x1 plus x2 plus x3 equals 1. Mod 2. Okay. So what's a simple polymorphism of this?
Linear equation and even, I'm sorry, odd number, even number, is it? Odd number?
Odd number, yeah, because you have a 1 equal 1 here. So if you sum any odd number of satisfying solutions, you get a new satisfying solution to the equation. Okay? So f just being x or k, where k is also odd. Okay, so you can write this thing Paul Boulevard, polymorphisms of R, and you can also write polymorphisms of S, which are those that are polymorphisms of all the relations you have. Yes.
So these are the symmetries in the lattice.
Yeah, these are the symmetries in the lattice. And in fact, I should have said as much when I talked about clones. I can define the lattice over them. We have 2 clones. B, C, is this defining this and this. Probably not so important for today, but just so you can understand that there's a lattice. And then if I share my screen again briefly, we can look at what post lattice is. So this is known as post lattice without the colors, but just the relationships between the sets. These are the sets of all possible clones that exist. They're all mapped. There's a large family here.
Should we think of n being fixed now, or
And like I say, number of
variables?
no, as I said, the clones they don't have a number of variables fixed.
Is it obvious like it should be only finite?
They're actually, I don't think there's a finite number of, there isn't a finite number of them. There's this dashed line. It's a hierarchy here. There's a k for every number, fixed number k.
Oh.
There's a hierarchy here from S1 S1 k, S1 k plus 1. But they're all log space when you look at the corresponding CSPs when we do. Okay. I guess I'll leave it at that. Leave it there. Before I can just share another screen. It may be helpful. I'm in the wrong place now.
Sorry, so I missed what happened with that intersection. What was the deal with it?
It's just the lattice.
Okay, the lattice
Yeah.
Yes, yeah.
And here's how you define all of them. We're not going through this, but just so you know. And here, in fact, all Boolean functions, as Jonas mentioned, and monotone functions, we need the zeros and ones.
Will this be on the exam?
No, I just had it. Yeah. Because it's relevant for the proof. Okay. Because we want to go until fourth here. Is that the goal?
I mean, it's somewhat flexible, but
What?
yeah, 4:15. It depends on inspiration, perspiration, desperation, how these combine.
Okay, let's see. So the first thing if you want to show the dichotomy, you want to show, the upper bound and lower bound first. And the first thing we have to do is show that three-horn set. So horn formula, though, find them is here monotone size poly. Okay. And then we will also construct some generic reductions in that lattice. We'll look at the sets of polymorphisms of the relations here and show that all of those guys that are above the polymorphisms of the relations of the horn set reduced to this one. So you get an upper bound. Okay. So this is going to be just 2 n cubed plus n. 1. CSP H3, and H3 is going to be the relative in the relations RX1, RX2, RX3. So we have always at most one positive vector. Right? We can allow them to be all negated. We can also allow not x, or sorry, x. That's enough. So how do you compute this? We do a reduction.
So the definition of three-horn set is all negative three clause, a three clause with one positive literal only, or like a unit positive literal.
Yeah.
Okay.
That's enough for every hand clause you want to write. And we do this by a reduction to the gen function. Which is in monotone size poly by a paper of Raz McKinsey. It's not hard to see, we'll discuss it. So what's this gen function? So n cubed equipments, and you can interpret this as triples, right? With a set of triples. You put a set of triples. And you accept if the let's say the special element, let's say the n, is in the set S. Brackets n. And where S is generated as follows. So you have one axiom, so put one in S, one axiom, and then for I, J, K is in S, in T, and I, J is in S, or in S, and K is in S. Okay, and you can compute that. Does it make sense then? This is like the triples are saying rules. First, saying that the first two entries are there both in the set, then the third one must be as well. Also monotone function, because we're just giving more rules for more chance of n being in the set at the end. And the way of computing these monotone circuits is just by some iterative process. First, you're let's say you're keeping this vector, which is characteristic vector of S. First, just one is there, and then you apply all the rules of all the rules that come from the triples. Then your characteristic vector will potentially increase its Henning weight. It has to stop at some point because you have Henning weight. You have n entries. And so you can just do that for n steps and look at the bit corresponding to n and see if it's one or not. And the rule is just saying just an end. This is all monotone. You asking?
No.
And this is, you can perhaps see that this is connected to the three-horn set because these here you can just see as x1, x2 implies x3. These here you can see as so in other words, this is a triple 1, 2, 3. This here you want to say that you can't have x1, so 1 is not in the set, 2 is not in the set, and 3 not in the set. And here this is just kind of putting it as an axiom, just saying that say psi is 0. So basically you just take, these are going to be a set of triples. Maybe you add 2 more numbers here. One should be the special one here that's not going to be connected to the variables, and then another one should be the special here.
I didn't get the
Yes.
all negated clause. So you're requiring that none of them are allowed to be in it?
Yeah, because if they're all in S,
I agree, if they're all in S, we're in trouble, but is this an or an and? Because you seem to be saying that none of them can be in it.
yeah, it should probably mean it's
Or do you want to give an element for each little instead of a variable?
yeah, I want to give an element for each variable, right?
Variable, yeah. Then seems like the second kind of relation in H3 is problematic.
Yeah, but couldn't you just I'm not trying to make like a manual reduction to gen, just I can call gen many times if necessary.
But we believe this is the way.
Okay, maybe I have a little mistake here. Let's see.
It seems to
Why
me
do you have the negated?
Mhm.
I'm also wondering why do you need the clause with 3 negation? I don't.
Oh, because
didn't
otherwise
have
it
that.
will always be set, right?
they're all variable true.
Otherwise
Yeah.
it's a very boring thing.
Yeah, you want to be able to have this thing.
Like if every clause contains a positive variable, then the formula is satisfiable, right?
But usually you would only have like not xn. And not have like. This one.
So you're saying maybe instead of this, you could just have the not xn,
That's.
not x. Maybe that's true. Maybe that's enough. But I can't do this online.
Yeah.
So sorry.
Some way of doing it, yeah.
There's there's some way of doing
And the
it.
bottom one you could have, it could be 1 I. It could be the triple 1 I.
Yeah. That's the other thing I would say. This is going to say that you have this 1 1. Yeah. The axiom is always implying the guys that are just X. And then in the end, let's see if we have this, or perhaps actually probably should be not X, only not X. Then you just check whether you're generating one of those guys. Then if you are, then it's unsatisfiable, and then you accept because you're accepting it's unsatisfiable. So accept whenever you're generating one of those guys which are in the set of those that say you shouldn't be generating them. Yes.
Oh, yeah. That's the same. I mean, that's good case. You're saying like actually a yes instance for gen will be like an unsat instance for the formula. Is that what you're saying?
Yeah.
Okay. So then we introduce like new, if we have n variables. Firstly, we have a dedicated like some kind of the gen 1 is some special element 0 or something, and then we have variables x1 up to xn, and then I guess we have their negated buddies, which could be n plus 1 to 2n, and probably each negated clause will give me 3 such guys. And for n plus 1 up to 2n, I will then, for every such j, I will have the triple j, 2n plus 1. And if I can't generate 2n plus 1, then that's like the gen n, and that would mean that I'm propagating to a contradiction.
Yeah,
something like this. Then that makes
good. All right, so this is something like no. So now we want you to understand. So this is for the upper bound with your set. So what do you use all this machinery of polymorphisms to get upper bounds from other CSP problems? Basically, what you want to do is revisit the groups of the Schaeffer's dichotomy, and
I think you can try the eraser also, like I did get it to work to some extent. One minus epsilon eraser.
right. So we want to revisit those proofs of the Schaeffer's dichotomy and check that all the reductions can be done in monotone way. So we may need just a few more facts or a few more observations before we finish this part. So maybe we could just the upper bound, please. So we define this. We have a set of finite set of relations, and cock is going to be the conjunctive queries. So it's all the relations expressible as psi where psi is in psi is a yes formula. Set of constraint applications of S.
Always K and L related now?
Just arbitrary constants.
Arbitrary constant.
So these are a relation. So yeah.
And the relation is over x1 up to x.
Yeah,
Okay.
this is the relation. So not okay. And then you make an existential quantification saying that there exists some y1 of yl, which will complete this assignment to the variables, and which have to satisfy this psi, which is an S formula. So yeah, all the
kind of NP version here.
yeah, I mean, yeah.
Or maybe we'll see how you use it.
But that's formula, formula in S.
Yeah, the formula, there's a constraint, a set of constraint applications from relations in S. So one of the lemmas, crucial lemmas, is if you take the set of relations here, which are conjunctive queries of S1, if they contained in the conjunctive queries of S2, then you can reduce CSP set monotone way to CSP set polynomial.
And reduce monotonically.
Yeah, what I mean here in more simple ways, like many one reduction, and you are really kind of maybe all your output bits are just an OR of the input bits. All the bits of the reduction are computed by an OR of the input bits.
The M is for many one or is it one?
Here is not, here is many. This is not so interesting, but it's kind of like just exploring the definitions. So what's really happening is if you take some formula here, or rather, yeah, from formula here, it's going to have some constraints. So let's see some constraints here. Here's some constraints of F. Since it's a application of it's an application of relations in S1, and you have this relationship here, you can write this constraint as this sort of extension over some other relation in S2. And then you can simply erase the existential and just put this very constraint here that you know that exists because of this containment. Finding it may be difficult. But I'm perhaps I should say that I'm really talking about, I'm only caring about non-uniform reductions. There exists one.
We should have another subscript.
Sorry?
We should add another subscript to the symbol.
Oh yeah.
But CSP set for S1, that just, I'm a bit confused. That only contains like constraints over X variables. Are there any, like if I get an, oh wait, yeah,
N variables here, that's what you're saying? Or
variables, and these
S.
variables are what?
Sorry?
Like I don't see where the
New variables.
I see where the Y variables would enter in S2, but are there like these Y variables also in S1?
No, the Y variables, they're added. That's why you get this blow up of the number of variables. Because you know there exists this relation, and there's this Y1 up to Y well. here. So
Yeah,
you just
but you're starting with something that is in not you're starting not with something that is S1, but that is for some reason is coq S1.
no, you start here. The statement we want to prove is this one. So you start with something in S1, but S1 is a coq S1.
Yes.
Well, that's true. I actually could have just written S1 containing coq X2.
Yeah.
That's true because this coq is idempotent is in monotone. So that if I get this, I get the other thing. Yeah.
Yeah, I was confused why
Yeah.
you needed this first coq, and you were saying I can have it or not have it. It doesn't
Yeah.
matter.
Yeah.
That much.
Yeah. So really, you're just adding a bunch of equations, and then to know if a certain equation is going to be added, you just do an OR to see if the equations that would add it are in the system. It's just a more. That's why you get this one.
Does this depend on the size of, or should I consider K and L both as constants?
Yeah.
So that poly n depends on K and L.
Yeah. Yeah.
Do we know anything about the size? Oh, you're saying it's non-uniform, but it's like small. It's like it's a big. Basically, it's one OR per bit.
Yeah.
In the S2
Mhm.
thingy. Okay. But it might be hard to compute. Or like that it exists.
Yeah. Oh, it's yeah.
Maybe one last question that is annoying is that I really want to know if that poly n is something like n to the L. At least, or if it's really annoying, then just skip.
No, it should be. I was thinking. I should think it should be L times N. No. Let's say if this L are the extra variables. Would you add? Maybe you wouldn't add extra variables. These extra variables for each possible equation. No, I don't think. I don't see why it would be NGDL. Why do you think of NGDL?
Maybe it's because I misunderstand. I mean, the definition of x1 to xk in per se. Should I think of x1 to xk a specific subset among n variables, or they are just abstractly, for example, 1k is 3.
Yeah, these are not. When I write this, I'm writing constant. K is constant, and it's not like on the variables 1 up to n. This is really just the relation itself.
Okay.
Yeah. Right. So we have this observation. And maybe now this is not so satisfying a choice of result to show the proof of, but there's some dilemmas that were proved back in the day. We showed by companies that show that if this issue which is in the lattice is contained in the set of polymorphisms, then S is just the contained in the conjunctive queries of or 3, 1.
Do we know what E2 is? Do we need to
E2
know?
is the end. So it's really you're combining solutions with end, basically. And that's what you have for
So basically, what the following things should be a polymorphism. I get 2 valid inputs,
Mhm.
and I just do bitwise and I should
Yeah.
get something valid.
Yeah.
And I want to provide any intuition for which kind of beast this is a polymorphism.
Well, what is written here is these polymorphisms for Hartford. So, and moreover, anything that satisfies this is basically for. So, let's say
So I'm just trying to unpack the definitions.
x1, x2 implies 3. So what are the satisfying assignments? Or let's let her write it like this. The satisfying assignments are everything except the 1, 1, 0. Right? And you check that this works. So
And now you're saying, well, basically, if any premise anywhere is false, then I'm off the hook. But if all premises are true, then since I'm in the relation, then both consequences are true.
Yeah.
That's all good.
Yeah. And this lemma says, okay, so E2 is our polymorphism is using a set of polymorphisms of form, but it's saying even more, it's saying that if it's contained a set of polymorphisms, then this set of relations is contained in conjunctive queries of form.
Which sort of means that I can
Write it as a horn.
write it with possibly with the use of extension variables.
Yeah.
I can sort of write it as well.
Exactly. That's what it means. So then to finish one of the parts of the proof.
And is this like obvious? If we just think about it, 2 minutes applying, we figure it out immediately, or
Yeah, I mean it's like 1-2 paragraphs. It's not
Okay.
So just go back here to the lattice. Whether I should show it into this. So you see, rather the dichotomy. E2 is here the most difficult one that is computed in monotone size poly. So the theorem I'm going to show is really the upper bound, at least for the right hand part. If E2 is in the polymorphisms of S, so really this is as we were discussing before, these are like the set of possible polymorphisms. Then CSP set S is in okay. So I'm just saying if the set of polymorphisms are above E2, contain E2, then is in monotone size poly. So to finish,
Is it easy to understand how these polymorphisms will be used? I mean, will I somehow, should I think of this as a derivation system where I'll take my input and then I'll use the polymorphisms to say, well, if all of these are satisfiable, then let me generate a bunch of other constraints that are also satisfied. And then at some point in time, either like I get a glaring contradiction and then I know the answer, or otherwise like I saturated everything and I didn't run into contradiction, and by some argument that means that I'm consistent. Or like, does the question even make sense?
I guess the idea is we're gonna do that thing we did of expression with extension variables. And let's say we are anywhere here above E2, and what the algorithm is going to be for this guy, or even for this guy. We're going to show that we can reduce it to the horn. So we had this. So we are going to add all these equations with possible extension variables, and then we're going to apply the algorithm for horn, and that's going to get back satisfiability or not. I don't know if that's what you're asking.
Not quite, but I think you kind of asked. Yes, okay.
Because you were asking an algorithmic question.
Yes, I was asking but
Yeah.
you're saying okay. It's not fully satisfactory because there's like in your reduction there's a non-uniform step, right? Which
Yeah.
confuses me.
That's
So there should be like a uniform way of doing that.
There is. I didn't think about this. And in fact, the exposition I was reading really didn't care about, didn't seem to be bothering about saying that this is non-uniform or not. It seemed to me that it should be non-uniform. And since in my setting, this I was happy with this. I didn't go
So
further.
MP is not a uniform thing.
Sorry?
What is MP?
Is monotone size poly, yeah.
Oh, okay. So yeah, so okay, so we don't care about.
Into
Yeah.
that statement, but I think you should be able. I mean, yeah, this should be doable. This should be doable. I just didn't think about that.
Wait, so actually, with the way I should have monotone P, I should think of this as P/poly.
Yeah, monotone slash P slash poly.
Okay, I guess I was missing that. I was confused by missing the /poly, so I was thinking about the monotone version of polynomial time somehow. That's not the way
Okay.
to think about it.
Yeah. Okay.
Sorry about that.
No problem. All right. So, how do we finish this? And everyone, yeah, we'll see. Let's suppose E2 is in poly S, then we have this. Then, because as I said, this is idempotent and monotone, conjunctive queries of S, and then conjunctive queries of H3, and maybe some theorem I just erased. Right? It's just then I just reduce the SP set S to R. Yeah, it's really just unpacking the definitions in this case and using this crucial observation here that you can express those set relations with queries over one.
And horn set you were in turn using by solving Gen?
Yeah.
Okay.
Maybe you could do directly, but
And Gen we were solving just by basically like taking the transitive closure. Like if first I know one, and then by one rule application, what can I generate now? And then I just maintain after, like the kth layer is after k rule applications, which integers have I generated, and then I know after n steps I've generated everything. And clearly like a monotone circuit can do that.
Yeah.
And then there was a way that we talked about to take a horn set problem and sort of mentally turn it into a Gen problem, and then write the circuit evaluating this, and then interpreting, I guess, flipping the output bit kind of sort of in some sense.
Well, you're monotone, so you don't want to put the output
but
because it's a stack except if it's unset, so it's already what you want.
okay, so you set it up. Okay, good. Yeah, and then this other problem that we have we're first writing it with existential variables, somehow writing that as a Horn formula, and then writing that as a Gen formula, a Gen problem, and then plugging. Yeah, okay.
Yeah. Just to finish what you would do with for the green part, the lower bound, right? Literally, what you want to say is, if the polymorphisms of S is below L3 there, then the monotone complexity, monotone size of CSP S, yeah, is large. And yeah, you do a reduction from Trixor set. Now you look similarly as there. We identified here with the E2 with the relations, the Horn relations, and then here we identify L3 with the which is basically linear those they are invariant under some linear functions. So you find the Trixor set here, and then you do the reductions by some other lemma that you show that you can do in a monotone way. You have to show that polymorphisms of S2 in the polymorphisms of S1. Then you reduce SP set to S2. So in other words, yeah, if you are below, then the one above reduces to the one below. And since you can identify Trixor set here in L3, you get a reduction from to L2 and to I2, right? The lattice there is really L3, L2, and 2, and I2. Someone else connects to here. And that gives you the bound.
And the fact that V2 is pink requires a separate argument that you're not telling us about?
The V2 is anti-Horn. So it's really the symmetric of this.
Oh, okay.
So at most one negated literal, and it's the same thing.
And then there's also D2.
Where's D2? Oh, D2. Good question. Oh, yes. D2, I didn't talk about that. D2 is really just connectivity. So it's really, you can reduce all of those to conjunctive queries over CNFs with two CNFs. So you solve the two CNF and then two CNF problem again. Right, I guess.
But there's no relation between B2 and B2.
No. Yeah, it's separate.
Because you only have two CNFs. Because you could have two positive or two negative.
Yeah.
Okay, yeah.
Good. I guess that should be I could go talk for hours, but probably that's enough for now, unless you have more stamina and interest. But
let's say that the discussion could go on, but maybe this is the point where we switch off the recording. Okay, a good opportunity to ask questions, comments, or protests.
Yes.
Maybe I should look through this out in my mind or by myself, but if you could help me a bit better. So I'm thinking of this reduction that you just wrote in the previous board. That is the cock of S1 is in cock of S2, then to solve a problem about S1 satisfiability, I can reduce the problem, this task to solving the satisfiability of an S2 instance. I would think of that, given me a S1 instance, what does the input represent? One input bit that is 1 represent, okay, this equation in S1 that is realized on these variables is given. And how do I think that I reduce this to something about S2? To simply put, I have the input of S1 instance. What do you do to those inputs?
Okay, the inputs, right. Let me think for a minute. So maybe what I want to do is you have this relations in S2, as you said. And in fact, you can have like N to the L constraint applications of those. Maybe you add extra variables for each possible constraint application. Then it would be N to the L as I had suggested first. N to the K, actually. Extra variables. Because you don't want the variables to interfere with each other every time you do the extension variables, right? So you do an extension variables for every constraint, maybe. Maybe that can work. I think that's one of the ways of doing it.
We're saying that for each one input bit, I create a bunch of new variables. And for different one input bits, those input variables are those extensional variables are fresh each time.
Yeah, maybe that would be the most wasteful way of doing it, but I think it would be true. It still work. But you keep, of course, you keep the other variables, you keep the same because you want the system to denote the same thing.
If you use fresh variables, I think I don't need into the other. If you use one input, it's just new node will be one because fresh variable.
You said you're saying you think it's wasteful to create fresh variables for every input.
For every input, you do need fresh variables, but I guess you don't need to go through into the K many possible choices of these variables.
Oh yeah, no, yeah, but you have N to the K many inputs, right?
That's you're talking about the input size.
Yeah.
Right. And I'm thinking of the blow up of the when I do this reduction.
Oh yeah, yeah, that would be L times N. That would be if you're adding L variables for every one to enter the K, so that would be L plus 1 times enter the K. So that's still a constant times the input. A constant number of variables extra. Constant factor, constable factor on the number of variables. Good.
Just one more question, which you, I guess, already answered before, but just as a recap, like where do we go from here? Like, the next big challenge, where are you headed? Like, what do you want to do?
Good. I guess this is basically this dichotomy is really in the Boolean part is complete.
Okay.
Everything that could be known here that I can think of. So not really, so you could refine those. But for me, more personally, and it could cook up so many other directions. For me personally,
You mean you can somehow quantify the polyness and the epsilon nest?
yeah, yeah. So one deficiency here compared to the most advanced CSP literature is that the most recent CSP dichotomy is for not only Boolean alphabets, for any non-Boolean alphabet, any alphabet. So can you prove a dichotomy for monotone circuits computing, solving CSPs over any alphabet, not only Boolean alphabets? That's not known, and we would have to really go through the CSP dichotomy conjecture, maybe, or maybe there's an easier argument to explore.
What about like looking at bounded depth?
What do you mean bounded depth?
Not monotone circuits of bounded depth.
Mhm.
Like with some of these classes falling for there, is that one way of having more
Fine-grained.
fine-grained?
Yeah. So even here, I can say that this is in N situ.
Yeah.
Actually,
But probably,
if you go all those are N situ.
okay.
So you can do that much fine-grained. So that's
Okay, you have
yeah.
some fine-grained there.
Yeah.
Okay.
But for me, I think the most difficult and most interesting question is really the one I talked at the end of the first part. Is really Grigni and Sipser's question. Monotone function is 0, super polynomial size, monotone complexity, and more ambitiously go all the way from AC0 to exponential monotone circular bounds. I think that would be very interesting as well, and I think that's a basic important challenge in understanding those models.
Is, for example, Sipser's function himself, I mean, the function named after himself, is that a candidate for?
No, because it's computed by AC0 monotone AC0 as well, because it's just alternations of words and ends, right? It's Sipser's function.
Yeah, sorry. If I add negation, that's not necessary, or at least I don't know whether it's monotone.
Yeah, that's the problem. Well, those Sipser function was used for some kinds of, if I'm not mistaken, separations in that sense between monotone and non-monotone world, but only for like TC0 kind of monotone majority circuits, monotone threshold circuits. But it's not a candidate for that problem that I'm talking about, but just as
And maybe the last question, what are some natural monotone functions computed by general HT0?
that's a really good question. That's what we're trying to find candidates for. I think one of the hard things is really to find candidates. One of my approaches at the moment is really to go through this higher class, which is log space, or even non-deterministic log space, and monotone functions there, and by padding get something AC0. But then you require the exponential monotone circular bound for that to carry through. I think the odd factor is a good candidate, but then proving lower bound for that implies also proving lower bound for perfect matching. Other candidates that I thought about discoding theoretical constructions that I did not mention in this talk, but we can discuss offline. Variants of Andreas function. Good.
Yeah.
Thank you.